Uh, Thanks, Fan, for a nice introduction. I'm very much honored to be a speaker here, especially 1 hour speaker. So it's not very customary for statisticians to give 1 hour talk. Usually our talk is like 25 minutes and so on. So thank you for staying here for 1 hour, first of all. And then I know it's hard to focus for so long. So I thought I would give a more or less overview of the topics of Bayesian linear regression. My real focus actually is for variable selection in groups. If you have multiple groups and you want to select the whole group instead of individuals. But I thought for 1 hour it's probably not enough, so I will just give a whole interview. So I actually start with the Bayes rule. So many people, most of my friends here, of course, it's not for you, but for some students or people who are newly into statistics or data science, I think it's worthwhile to know this one of the basic methodology or the way of thinking, the way of dealing with uncertainties is using the Bayes rule or Bayesian method. The so-called Bayesian method start with the Bayes theorem. Bayes stands for this Thomas Bayes, who lived about a little less than 60 years. He was not really a mathematician, but he sort of math is his side interest. He's mostly a priest who are doing sort of all these religious things. Actually, the Bayes theorems, he never published that. He wrote this down on a scratch of paper and put it on side. He didn't really regard this as something a big deal. And later on, his friends actually found his leftover papers and then published that. So it's an interesting story. So it's only known a few years after his death. And there was a common joke that Bayes himself is not a Bayesian. Bayesian stands for those people, statisticians who use Bayes rules to do inference. So Bayes himself is never a Bayesian because he didn't really do inference. But if you look back, he actually is somewhat a Bayesian because he was trying to do the so-called inverse problem. That is, for example, if you toss a coin 10 times and observe like 8 heads and 2 tails, and you estimate what's the probability of head in the next row or something like that, or what's how do you think about the coin? So what's the property of the coin? And in the more abstract formal way these days, we model that as Bernoulli random variables, and then we use Bayes theorems. He was actually doing some kind of mental exercise. He was thinking about the billiard board, like a pool, and then there's a white ball. He just randomly throw and look at where its location on the table, and then he threw like 10 other black balls and see what's their relative positions. And that's his mental exercise of making an inference of what's the relative position of this white ball in comparison to the others with the black balls. But if you write them down, it's very trivial. It's really just the conditional probabilities. The real person who actually took this Bayes rule into actually inference problem was Laplace. Laplace was the one who actually first advocated using this conditional probability to do inference. So the Bayes rule is really like this, and these are all generic notations. P, so you shouldn't understand it as one particular function is really just probability law. So sometimes I don't write the P, I just write the parentheses. So this is saying that the probability law or your knowledge, so these days if you want to do learning, we represent knowledge by probability distribution as well. So you can regard that as a personal uncertainty or personal knowledge. So X is the evidence or the observations. Theta is something about world. So like the probability of head for the coins or other things you are interested, but you didn't observe directly. but it's related to your observation. So that's where the mathematical model may play a role. And if you want to update your knowledge about theta, this gives you updating rule. That is, p theta is called prior distributions, and x given theta is called the likelihood. And this is a simple conditional probability, but you revert the relative positions of theta and x by using this rule. And it's actually very intuitive and appealing to human cognition. And many psychologists actually are trying to test whether human learning is really following Bayes' rule. So this is, if you treat this as your current knowledge of the world about whatever, like if you see a person, you look at how he looks, how he smells, and you say that's your prior. Then after you spend some time with him, then you have to update your knowledge about him. You suddenly realize this is a jerk or something like that. But this is sort of your prior, then this is your data, then you update your knowledge by likelihood weighted by prior or prior weighted by likelihood, whatever way you want to put it. It's really Bayes' rule, but I think this proportional sign is very important. Many people did not realize that, but it's proportional in the sense that as a function of theta, this px is constant, and then if you think about the function of theta, these are reweighted. So they're reweighted by your evidence. So that's the Bayes' rule. That's very simple rule, and it's intuitive. A nice thing about this particular framework is that put everything into a probability structure. So you only need to do the so-called estimation or inference by using probability rules. So that's the nice part. But unnice part is that's really what have actually almost smashed down, almost killed the field of or the idea of Bayesian analysis. Is many top statisticians in early 20th century, like 1901 to 1920s, like Fisher and Pearson and so on. So one of the biggest argument against this is that we sometimes do not have a good form of the prior information. So once you don't have or are not willing to put on a distribution for your unknowns, then this becomes problematic. You cannot invert this relationship without having a prior. So that's actually what Fisher and Pearson have in common. They're all against this. Although they hated each other, they actually fought each other a lot. But this is what they have in common. So it's like I think Fisher has made, he is regarded as a father of the modern statistics. He actually founded, because of him, I founded the Department of Statistics for many other departments later on. Well, at least he and Pearson together has a huge influence for modern statistics. So in later part of his life, he actually realized the sort of fundamental usefulness or fundamental sort of structure of Bayes' rule. And in the later part of his life, he was trying to use the Bayes' rule without having a prior. So he was trying to make this inversion happens without giving a particular prior distribution. But as you know, he actually tried very hard and didn't achieve much. Didn't do very successfully. Although he introduced this concept of fiducial probability or fiducial statistics, and accordingly, actually, so I suddenly forgot name. Tukey, John Tukey actually followed him on that problem for many years, and eventually he didn't. He also wasn't very successful. Of course, John Tukey is a great applied mathematician and statistician. And he was the one who actually put up the name of data science and trying to do everything from data. And he also is really mostly known, well, most well known for his fast Fourier transform. So anyway, he is a true genius. The problem of genius is that he actually destroyed the Department of Statistics in Princeton. So because he's too good. He just doesn't want to hire anyone because nobody is as good. So that's why he killed the department. Anyway, so okay, I will try to apply the Bayes rules to regression problem, especially dealing with this high-dimensional problem. So linear regression in high dimensions, as you know, this is a typical formulation of in the matrix form of linear regression problems. So beta is a vector of p dimensions. You can regard this as column vector. And you have n such observations. So, so X is n by p matrix. And so the typical classic statistics, usually n is much larger than p is 3 or 2 or and so on. So that's when I was in graduate school, they talk about that. You never actually had a problem with p more than 20. But these days, if p is smaller than 1,000, you don't even want to mention that. So now people talk about so-called high dimensions, p is much larger than n. Like in a lot of genetics problems, p may represent variations, genetic variations, which can range in millions and so on. N, like number of individuals, maybe a few thousands, or even in large study, 20, 30,000. That's quite a lot, but p is another scale. So that's sort of the mental image. Actually using this type of methods, most methods are not really able to handle like n is a few tens of thousands, a p is a million. I don't think any the so-called high-dimensional methods can truly handle that. The typical approach is do some kind of screening first to shrink down to around reasonable range, but nevertheless, it's okay to think about that. And nowadays, when people talk about large language models, all those things, and a few thousand is really a very, very tiny number that easily talk about like hundreds of billions of parameters and so on in these big machines. But if you want to understand anything, those are great experiments. So once David Donahoe, one of the best theoretical statisticians of this century, he always think about this deep learning, all these things as experimental science. It's not mathematical science. Because you can't really do anything mathematical about them. You can experiment with different structures and so on. Or you can call them engineering science. Okay. So that's the structure, and the question is how to make inference. And the standard approach typically introduce some kind of penalty or for theta. In other words, sometimes they use theta, sometimes they use beta. It's a little inconsistent, but hopefully it's okay. So this is really saying that if you have very high dimensions, you want to have some kind of regularizations. And in deep learning, people talk about implicit regularizations. In this kind of simpler model, even simple, you still need to put some kind of regularizations. But if you think about regularization terms, I think it's kind of too arrogant. In other words, what do you regulate? Who are you to regulate, right? But that's if you're Bayesian, it's much more straightforward. You really just put a prior. So you have a prior information or your prior assumption on the structure of your parameters. You put it down as a probabilistic form. Then you just use the Bayes theorem. So that's logically more coherent and more modest. If you're non-Bayesian, you talk about regularization. So that's the typical word. There are so-called L2 regularization or L1 regularization or some other regularizations. And this one actually was introduced very early just for avoiding singularities of the matrix when you do the inversions. And this one is for so-called sparse solutions. which I regard this as a mathematical accident. It's nothing particularly magic about L1. It's really accident that give you so-called sparse solutions. There's nothing particularly attractive. Well, there's one attractiveness, which is computationally easy. In other words, this is convex problems, so you can solve them in a reasonably fast way. But I don't think they can handle like millions of dimensions problem. They probably can handle like thousands of dimensions and so on. SCAD is one introduced by Jianqing Fan and Renze Li, so which is quite popular. It's becoming non-convex. So this is like L, which one is which? I forgot. What, so this is sort of more like SCAD versions, and it's become non-convex. And as I mentioned, the base solutions are conceptually easier. That is, you have a models regarding your observations, how they are related to the theta, and then you put a prior on theta, and then prior on variance, and you write down the joint probabilities. That's it. So the rest is computation. And then the question is what kind of prior we can give. This actually takes some time. When you are first into Bayesian analysis, you just thought there's nothing really there. You just so that's why my thesis was really on MCMC because, well, what else can you do? You basically, the problem become computational. You only need to compute these posterior distributions. And if you're thinking about this thing is easily tens of thousands of dimensions, it's really hard to compute. One of the common strategies in the past like 20 years in the Bayesian statistical world is to develop tools for Monte Carlo approximations. So the Monte Carlo Markov chain Monte Carlo is one of the most popular approach. But later I realized actually the prior does need some kind of mathematical analysis for one to understand, because in most cases we know very little. So especially if we assume some things on a high-dimensional space, it's become extremely like out of our range of thinking. We don't really know what we're talking about. So it needs some kind of analysis. So there, I just summarized, there's a few classes of so-called shrinkage-inducing priors. In other words, these priors enable parameters to shrink towards zeros or to regulate them. And there's some one which is more encouraging more sparsity, some just shrinkage. For example, you can put a Gaussian prior on beta, which corresponds to the square penalty, because it's the log of the likelihood is the quadratic function. If you put that kind of prior, that really achieves the shrinkage, but that doesn't induce induce sparsity. I will mention a little later. So there's this type of hierarchical structured priors actually induce somewhat sparsity, not exactly sparsity. So if you want to be explicit in terms of sparsity in a Bayesian form, you can give this type of explicit prior. That's saying, okay, I think my beta is either 0 or non-zero. So I give a 0 certain probabilities. So that's the discrete part. So this is the degenerate density distribution at 0. This is famous Dirac function. And this is some kind of continuous function of beta. So this is very explicit. That's very almost like put your own story into a mathematical form, saying there's a certain probability to be 0, certain probability to be non-zero. If it's non-zero, it comes from some kind of prior distribution. But this one actually can be a tricky one to choose. So what prior you should choose can be tricky. And there is a slightly easier version which is called continuous mixture, which means that even when it's you don't really use exact 0 to represent this 0 coefficient. You use a distribution which is more focused on zeros with a small variance to represent that sort of small coefficients. The difference is it's not too much, but this one is continuous, make computation a little easier. So you can use derivative to find mode and so on, at least conceptually. But it's not very much different. Even when you are using derivatives, you may have multiple modes and you may get stuck. So anyway, so for the continuous shrinkage prior, there are a few interesting special cases. So they can be generally formulated in this way. There's some hidden variance term and condition on which this is normal. And this variance follow another distribution. So if this distribution is just a constant 1, then this is just normal. But depending on what this distribution is, you may achieve different marginal distribution of this theta j. So for example, if this is exponential, this become a Laplace distribution. So if this one is half Cauchy, meaning that only positive part of Cauchy, then this becomes so-called Hausdruck prior, which become very popular these days. This Hausdruck prior is very interesting prior that somehow perform quite well. If you just do some empirical studies, this perform quite well. And there's some other things which are less popular. Typically, these two are most popular ones. And here, give you a little comparison on this. You can see this is the t distribution prior. This is Laplace, which is red. And then this black one, which infinite at 0, this is the Hausdruck. So what's the relative advantage? This really says, so this t actually gives too little weight on 0. In other words, the relative advantage of Hausdruck is once you are close to 0, you basically are shrunk to 0 very fast. If you are far from 0, because tail is kind of heavy, if you're far from 0, that doesn't really affect much. So in contrast, if you think about normal distribution, that's really just shrink almost proportionally. It doesn't really care how far away or close are you from zeros. But this one, you can see it have a shrinkage effect depending on the magnitude of your observation. If it's very close to 0, it's sort of nearly. So that's this infinite spike on 0 has that effect. Laplace is also not enough to shrink to zeros. So, but also Laplace somehow has two light tails. It will affect every estimate. So that's why you know that if you do lasso, you always have bias. If you have this Laplace prior, you also have this bias. But if you have, for example, T or Cauchy, you won't have bias when it's large, but you will not have enough shrinkage when you're close to 0. So somehow this Hausdruck prior is a good compromise of the two. And so this is the so-called continuous spike. As I said, you use a more sharper distribution on 0 for representing the 0 coefficients and the wider distribution for others. So if you mix them, you have a distribution like this. So again, this somehow depending on how wide you choose. If you choose it too small, it's almost like a spike. The computation can be hard. If it's too large, it doesn't achieve the effect of shrinkage. So there's a potential issue there. And the discrete ones, as I said, is just directly assume 0 here. So you don't need to worry about choosing the variance of the smaller one, which is good. And there's some nice theoretical properties like optimal predictive model selections. So they will select the optimal models. And also, if you think about this latent indicator variables, and this distribution of this gamma directly tells you the inference, whether it's 0 or not, because gamma j would be the probability of being non-zero, and 1 minus gamma j would be probability of being exactly 0. So it's related to the first advantage. But also there are quite some challenges. If you do like if you in this kind of high dimensional things, you can't do differentiations because of the discreteness, so you can't use like gradient type of methods here. It has to be somewhat like combinatorial optimization. But we all know combinatorial optimization is almost impossible to solve in any reasonable analytical way. So you can use some kind of Monte Carlo approach. And this is just one demonstration of using Markov chain Monte Carlo for a not too hard problem. You can see this kind of zigzag and take a while to actually get to the good regions, and also it can jump back again. And another thing which is more general in the challenge, you can see these different priors require different codings. Although the normal, the Gaussian regression model parse is the same, but if you use different prior, you have to code them differently. So, and some of them are continuous, like Hausrule, and you need to compute the priors, posteriors. And some of them are like discrete combinatorial. And if you're a practitioner, you may want to try different priors. Actually, that's a real issue in some of our genetic studies. Some common diseases are more sort of, their genetic components are more sparse than some other diseases. I forgot which one it is. There's some, obviously, it depends on a lot of small variants, small variations. They seem to favor more like models with fewer, with more common shrinkage, but not too much selections. But some other diseases, they seem to favor this heavily sparse models, in which case different priors may give you different effects. So that's one thing we thought it's probably good to have some kind of unified approach to take care of all prior distributions. So that's sort of what motivation of this work, which published about 2 years ago. We call it a neuronized prior to take advantage of neural network, but this has nothing to do with neural network. There's a little bit, which is the ReLU function we use to give some kind of activation term to that. So we essentially model the distribution of beta, or you think about each beta as random variable, as the product of two random variables. One is the normal, another is transformation of normal. The transformation of this normal can be nonlinears or linear. So for example, if we choose this as a constant, this just goes to normal. But if you choose this as another normal, for example, t is just constant and alpha is just, this one is just another normal. And normal times normal is actually equivalent to Laplace. You can get a very similar effect of Laplace. And if you actually can match different type of this activation function t to achieve different effects. So for example, if we choose this kind of ReLU function, you actually get this kind of discrete mixtures, because when it's zero, so it's all focused on zeros, when it's non-zeros, it's a product of some other things. So this actually can be very close to Hausrule priors, and this can be very close. This is really just a spec slab. So this is to demonstrate some QQ plot of the priors we generated from our formulations versus the standard, like Lasso prior, which is Laplace, and this is Hausrule prior. They're almost straight lines, so they're pretty closely aligned. This is like a spike slab priors, so this is really just very high probability. But these are simulated from data, so in fact you can't have a density here because it's all infinity. So a computational strategy. In this case, we can write down the prior distributions together with the likelihood and we directly write our beta into this form, so they can be written in this form. And everything is explicit. You can actually use a gradient-based methods to do mode finding, and you can also do MCMC type of algorithm. So we implemented a Markov-Chain Monte Carlo methods for doing sampling, and we compare the computational efficiencies of this particular. So there are two versions. One is a little more lazy in the sense of analytics. So another one we call it exact, where we figure out exactly one of the steps in sampling. Or this is like one-dimensional sampling, where we can do it as random walks or do it exactly. So random walk is slightly more efficient in terms of computational efforts, even you iterate a lot. But even in this case, even we do analytically, we labor a lot and we implement that, but that formula is actually more complicated than random walk, so it takes more time. So it's surprisingly that the more brain work doesn't pay off in this particular case. This is the case if you do the standard spike and slab, it's much less efficient. It takes a longer time, even for the simpler problems. Anyway, so it's just demonstration. We also have some, this is another example. And we also have algorithms to do posterior mode finding. So we call it coordinate ascent algorithm. You can iteratively doing coordinate ascent, and then so this is comparisons with some existing methods. People have been using like SS Lasso and the EMVS. These are developed by people, I think UPenn people some years ago, by Ed George and his students. And who, what's her name? She just got a COPS this year. Veronica, right? Yeah, she's very, very good. And I forgot. These are probably from some CS or optimization people. We can see if you do more this way, just demonstrate. If you do a few independent round of mode finding, they actually are not the same. They will be somewhat large variations. But if you use our method, we sort of all somehow goes to the same place. So it seems our method, there's no theory, we just demonstrate. It seems to be a reasonably robust way of doing mode finding in this case. Okay, so now we go to second part. So that's the introduction of Bayesian and using Bayesian priors for, yes. Yes. Oh yeah, good question. Thank you. We actually use this for some genetic studies in the past year with together with Taehee Lee from Changhao and also my former student. So we essentially use this, like we try the 3 priors for the same data, and then we use some kind of cross validations to decide which one is better. Yeah, in that case, we are trying to predict the polygenic scores. And in that particular example, there's something which is interesting, that in those data, you assume you only have marginal information. In other words, you only have single marker correlation. In other words, you cannot have the whole X. You only have correlations of each X and Y. In other words, you can assume you only observe X transpose Y. You cannot have the whole X, right? And of course, you won't have X transpose X, but you estimate this information from other source. And then you can still do kind of a regression type of answer, like X transpose X inverse X transpose Y, because you have X transpose Y, you can estimate X transpose X from other data, you still can estimate its beta. But to do Bayesian is a little bit hard. You can still do that because our posterior distribution also is only dependent on X transpose X and X transpose Y. But to do cross-validation is a little trickier. So we sort of have to make up some kind of split of the data in that form and then to do cross-validation. It seems to be reasonable to do cross-validation. But if you have the standard data, you could do cross-validation reasonably easily. Yeah, that's the that's only. There's a potentially is a empirical Bayes type of answer, so which is for the next part, but not for that. Okay, so this is we're dealing with linear models with groups of variables. The structure is very similar. So at first we thought it's just straightforward to apply Bayesian to do this, because instead of splitting beta into individual components, you split beta into groups of variables. Each group you can imagine is maybe 10 predictors in group 1, 15 in the group 2, and 11 in group 3, and so on. You have multiple groups, so you can imagine you have many groups, like 200 groups, and you want to select a small number of group of predictors. So it doesn't seem to be anything different, except it's group instead of individual ones. There are certainly needs for this kind of studies. Like one of the most commonly encountered cases is additive models. If you think about basis expansions, one variables can be represented by a few bases to represent nonlinearities. And then you have several variables, and you can do this kind of additive model to fit nonlinearities, but also have variable selections. And you may also have some kind of genetic data and SNPs, single nucleotide polymorphs within one gene. You may want to group them together, or you may want to group certain variations like genes expression in the same pathways or something like that. There are different reasons for doing group structured regressions. So that's the motivation. So the Bayesian approach is similar, as we said. You just try to represent your assumptions of this structure into a probabilistic form, and then you move on with the Bayes theorems. And there could be potentially ways. So there are G groups, and I assume only a subset of them have non-zero coefficients. And if we say it's non-zero, the whole group, so we assume it's non-zero. So we don't specifically choose them. You may actually further do variable selections within the group, but we didn't do that. So that's the assumption. You probably can just say, okay, S is a subset. You have a probability distribution of selecting subsets, and then given the subset, you say everything within the subset follows some distribution H. Otherwise, it's 0, and you have variance for G. But this one is actually a little awkward. It's pretty hard to implement because the group prior is not it's flexible, but it's not very practical to just think too generally. So one of the special way of selecting groups is at the individual level. You have for example, you have a binomial distribution. So every member has certain probability to be in and out. Then that gives you a distribution on the subset, which is the binomial selection. That's one very easy one, and it's also one of the most common ones. So so this is very generic notations of the likelihood times the prior. You can write the posterior distributions. You may just move on to do MCMC, and and you may just want to just focus on beta and sigma square and not S. You can sum them out. But you may do MCMC, so Markov chain Monte Carlo with everything mixed together, and then you just look at the beta and sigma square after you do the sampling. But it's well known that MCMC can be very, very slow. If you have a large number of groups, that may be slower. at least it's a little uncertain. It's not badly slow, but it's possible. I think in most statistical problems, MCMC, we say it's slow. It's not really that slow. It's reasonable. It's still doable. People just use that as an excuse to do other things. But we know, like actually for deep learning models, it become really slow. So people still sometimes do MCMC, this type of computations. And later on, they give that up, which is quite reasonable, but uses so-called variational approximations, which turns out to be extremely useful and helpful. Like the famous variational autoencoder actually make it quite feasible to do generative models. So as I said, this kind of binomial type of subset selection is quite reasonable, and the W is, you can assume the probability of in and out is known, which is maybe 1 over G, meaning like you expect only one variable, one group being selected. It's very conservative, but it seems to be reasonable. Or you can give a prior on this, and I think empirically giving a prior is slightly more flexible, better, in case that you specify W very much wrong. So if you give a prior, you can give a simple beta prior. Beta is a parameter we set as 1 G to the power of U. And in this case, we actually do not have to work with S anymore. We could directly write down the joint distribution of everyone, because each beta J is an explicit mixture of these two. But it's still not easy to work with directly. And the previous formulation of introduction this S, or the indicator of which variable is in and or out, is a typical way of doing MCMC, Markov-Chain Monte Carlo, to simplify computation, because once you know which one is in, which one is out, you can update their coefficients very easily, and then you can update all the parameters very easily. And once you have this knowledge of other parameters, you can redo this computation. So there are a lot of detailed difficulties of working with these discrete mixtures. I won't list all of them, as many of you may not be expert, but it's challenging. So it's like, as I said, it's combinatorial optimization. You basically have to randomly switch on and off each one of them and try all of them. It's like you turn on and off each of the variables. And if you have parameters, making it even harder. If you have a parameter, if you can integrate out the betas, but that's just turn on and off the subsets, it's reasonably fast. But if you have a non-standard prior, you have to carry both the discrete part and the continuous part. It become notoriously hard. There's so-called reversible jump MCMC and various kind of tricks invented, but none of them really works very well. Though you can publish a lot of papers, but it doesn't really work very well. So one of the trick, or one of the compromise, maybe as we mentioned earlier, you just replace the spike part by some continuous function. Then you avoid this kind of dimension jump issues in MCMC. You can do better MCMC, but it's, I said, it has own disadvantages. So we introduced a variational approximation method. Not that we introduced, we actually use this variational approximation methods, which was, I don't know who first introduced that. It must be very early in the 1970s by someone, but the people who made it very popular is Michael Jordan. Although I know for sure before him there has been people using this variation, maybe some physicists most likely. And Michael Jordan, as some of you may know, is quite a well-known guy in machine learning, statistical machine learning. I think he, by sitting in both stat department and computer science department, he actually take advantage of this by actually importing a lot of statistical thinking into this more engineering landscape of doing focusing on very large problems. I think he has the engineering mindset to work on really large problems, which is very important. I think our inner trained statisticians are more conservative. They only work on IID small samples. Although we talk about n goes to infinity, our infinity is typically 100 or something like that. But their infinity are much larger, so it's different scales. Anyway, so this variational approximation is quite simple conceptually. It's somehow become quite popular and quite well known. I think there are two components of this. One is this just trying to find another distributions in an easier family to approximate your target distribution using this KL divergence. And you know this KL divergence is quite a popular measure of differences between two distributions. Like people these days to do generative modeling always use KL to measure the target whatever samples, like millions of images as a distribution with what you can generate it. So that's one of the common ones. And KL divergence is reasonably easy to compute if you have the two densities, especially if one of the densities is at your control. So you typically write the one which you need to work with in as Q, and pi is somewhat your target. It's not very symmetric. That's one thing. KL is not ideal, but it's good in the sense that you can use your working density, which is the easy ones, as the one you can manipulate. So KL need an integral. I didn't write down the definition of KL. So it's if you have a distribution P and Q, it's log Px over Qx. I often write it wrong, so I may. So this is the KLPQ, I think. Maybe I'm wrong. So always. So this is the or QP. But so this one meaning that this is expected value under the P log P and the Q. So you can see that sometimes when you don't have analytical form of these integrals, you can always create samples from P and doing Monte Carlo approximations. So that's one of the nice things to have something you can work with. This is, or let's use this notation. Oops, this is nice. So let's use this notation we had, which is Q and pi. So this Q, this is, which one is upstairs? So I forgot. Is that Q or QX, pi x? So this is EQ and Q over pi. Okay. So anyway, so that's the general ideas and the computation. So this is one component, and I will introduce another component for variational approximation with the integral parts. If you have some part of your density you want to integrate about, you can use this variational approximation methods, which actually is a more generalized version of the EM algorithm. Some of you may know the EM algorithm. Yeah, I have always thought the EM was very strange algorithm. It take somewhat kind of twist. And until I actually see a paper by Redford New and his advisor Hinton, who was the famous Hinton, about thinking about EM algorithm as MM algorithm. So that's where I actually, so it's actually linked with variational approximation. So this algorithm is algorithm to find a good Q to approximate your target. As we said, the Q has a form we can choose. In this case, we actually choose just like direct mixtures. And also Q of sigma square is also the famous inverse chi-square type of distributions. but we still have a few parameters we can tune to make it fit better. The way to tune these parameters is the so-called iterative algorithm, coordinate ascent algorithm, which is you fix all the other components, their distributions, and you just change one component and see what is the best one you can have. And there is an explicit solution of that. It's not very hard. And then you can update that. In this case, because we assume a mixture normal, and a lot of analytical solutions are available. But if we assume some other priors, this may not have analytical solutions. So we introduce another one. And so if so these are the form for easy, for Gaussian part. So there's explicit solutions. But one of the parts, when we do the update, we need to evaluate the expected value of this log of h. H is the slab distributions we assume for the mixture priors. And for Gaussian, this is easy, it's quadratic. For non-Gaussian, this is not easy, so you don't have the explicit solution. In which case, we sort of are somewhat stuck, although you can do numerical approximation, but it's quite slow. So we introduce this hierarchical representation, or we utilize this hierarchical representation for other prior distributions. And this idea was actually borrowed from this Casella earlier work on Bayesian lasso. So they actually use this latent representation to represent Laplace distribution as a scale mixture of normals. The scale distribution is something else, like normal and inverse case gamma distribution or gamma distribution. So for example, this multivariate Laplace, because here, I forgot to mention that the challenge part of the group selection is each component becomes multivariate. So if it's a univariate, it's much easier to do this type of numerical approximation. But once you have multivariate case, that's where the group challenge comes in for Bayesian analysis. The computation is the real challenge. So we need kind of different tricks to overcome this type of numerical issues. So using this kind of latent representations can simplify the multivariate integrals into univariate integrals. Then we can deal with that univariate integral very easily. So that's so we actually introduce this so-called the new family of this mean field approximations and so on. Okay, so the last part of this analysis is to update the hyperparameters. In particular, we have two hyperparameters. One is the penalty lambda, which corresponding to the prior weight, and another is W, which is the relative probabilities of being selected or not. And so one of the principled way in Bayesian analysis is to do marginal likelihood computation. In other words, you want to find W and lambda to maximize this kind of integrals. But you can see this is pretty hard to do. So it's hard integral to do. Even if you use Markov chain Monte Carlo, this is not very easy. So to compute this kind of marginal likelihood. So here is the general ideas of variational approximation. So I formulate the previous problem simplified into an easier form. There's two parts of, so y is always observed. There are two parts in your system which are variables. One is the z, we call it latent or missing part. And theta is the parameter you want to focus on. And we want to find the maximum of this marginal likelihood, which is integrating out the z. So you basically want to do this. So this is kind of a very standard form in a lot of statistical analysis. You have some part you want to integrate out and you want to maximize that. So you cannot do it directly like gradient methods directly on L because L needs this integral. But of course, you can also do numerical approximations, but it's hard. So the key idea of using variational approximation is this. That is, I call it the important sampling plus Jensen's inequality. which is you can always write down these integrals as the integral with testing density p. So this I call importance sampling. You have a ratio, you change a different measure. So you originally is just trying to integrate out the z for this distribution, but you can do this. And you have a log here. Then this is inequality is the Jensen's inequality. You pass this log into this, you become this part. Okay. And now you can rewrite this because this is integral with respect to 2p. You have these two parts. And so now, so this is called the elbow. It's evidence lower bound. And this is the so-called, this thing is called the Lagrange function. And you can imagine an algorithm doing following. Given p, you want to find the theta to maximize that. So instead of maximizing this thing, which this integral, which we cannot do, we maximize this lower bound for that. So that's where the name comes from. And another iteration is once a given theta, you want to find the best p. It turns out the best p is the complete data log likelihood is the conditional, the predicted distribution of z given current theta. That's exactly the EM algorithm. If you find the best p in this particular formulation, you get the EM algorithm. But if you fix p at certain families of your convenience, you don't have the EM algorithm, you can't guarantee the best mode, but you can have pretty good approximation. So that's two parts of these formulations. Okay, so anyway, so at the end we have, we use this variational approximations. Because of the time, I won't give you any theory about this. So we sort of get some contraction rate for posterior distributions. We also, with some assumption, we have a contraction rate for variational Bayes distribution because the variational Bayes is approximation to the true posterior. So I still have reasonable concentrations, meaning that will, as you have large samples, you will concentrate on the true models. Here are a few simulation results compared to compare with different methods. And these are, where's the different methods? Sorry. These are different recording precisions. The top ones are our methods, of course. But anyway, so so these are just looking at the effect of different priors and how they compares. So we did the real data analysis and compared the precisions of our method and some available methods for the mean square errors and prediction errors in the cross validations and so on. Anyway, so very quickly, I review some of these Bayesian linear regressions and trying to explain the unified framework which enable people to do some comparisons. And also for the group linear regressions, we use a latent structure formulations to overcome some computational challenges. But I think some extensions to other models, generalized linear model and so on, will be interesting. So most work is done by Buyu. So the first part of work is collaboration with Minsu Exchange. And the second part of work is Buyu and Changhao. Changhao is now working with, yeah, so still student, but the other guys are in either startup or investments, which is a pity. So I hope you can keep Changhao there, Hongzhe. So is he your former student? Okay, thanks. Huh. Huh. Yeah, that's interesting. We didn't implement that. I think it's a reasonable further restrictions to say maybe within each group there's some kind of fixed and random effects type of models. Yeah. It's actually not. It's not faster. It's probably easy. Not faster. It's probably easier. Uh, right. Yeah, I think we compared the computation. I don't remember where it is. Um, yeah, our approach is quite reasonable because of the uh-huh. Yeah, the variation approximation is almost like a gradient descent type.